Not much.
No, not much.
That's
I
fine.
don't even like.
But it's very important to do some self-study.
You're right.
Yeah, it's very important. It will definitely pay off. Look, just try maybe 1 hour before bed, at least to reflect on whatever it is we do every Monday to Thursday.
Okay.
Let's
Except for
try the.
Wednesdays.
Hmm?
It's except for SARS.
Oh, Wednesday is going to have um, longer days.
Yeah.
Okay, that's fine. If I want to do this now. 55. Okay. We were on page 39 the last time, right? On Saturday. What happened? Oof. Go Sam. I don't like when the internet just goes down on me like that. It appears I got disconnected there.
I can still hear you.
Oh, okay, cool. So, have you got your learning guide ready?
My learning guide is ready on PDF.
All right. We're going to start with collisions. Um, so let's think about a scenario where we're playing pool, right?
Yeah.
And it's we're left with the cue ball and the black ball on the pool table, and we now have to study that as some form of collision. So the one thing that is described at the beginning of this part of the chapter is that the net change in momentum is 0 for an isolated system. So the change net in momentum for an isolated system is 0. That uh, that means the momenta of the individual objects can change, but the system as a whole, the momentum is isolated. So let's think about it this way. If you have the two snooker balls, the cue ball and the black ball, if they're both moving toward each other before collision, each one has its own momentum.
Yeah.
And even once they've collided and now have changed direction, they have changed their momenta, but the total momenta of the system of both cue ball and black ball before and after the collision remains constant. So that means it makes sense to define the total momentum at the beginning of the momentum of the problem rather as initial total momentum P subscript Ti, and that includes the momentum of object 1, which is the cue ball, and the momentum of object 2, which is the black ball. Right. And then the final momentum is also the second momentum of the cue ball and the second momentum of the black ball summed up. So, in other words, momentum conservation implies that no matter what happens inside an isolated system, the total momentum before a collision is the same as the total momentum after a collision. Right, so I'm just going to make a note of that. Momentum conservation is the same. Oh yeah, implies that, implies that total momentum before a collision is the same as total momentum after a collision. And this is the momenta, plural, of each of the objects in that system. And now we call that system, sorry?
Yes, I'm listening.
We call that system isolated because even though there might be other objects at play, but if we're just focusing solely on two objects, then we are isolating that system. And we call it a system because it's now two objects, each object with its own momentum contributing to the total momentum of the system itself. And the mathematical way to express it is to simply say momentum total initial equals momentum total final. Right, so before and after a collision or explosion, the total momentum is the same. So now we're going to explore the two cue balls example. We've got one object of mass 1, we'll call that the cue ball, moving at a velocity of v initial 1, right? So the 1 is to indicate that it's for object 1.
Yeah.
And this cue ball is on that nice cushioned mat, which is frictionless. And it's moving in the direction of another object, which is a black ball. That black ball also happens to be moving in the same direction. Towards the cue ball. So its velocity is velocity initial 2. The 2 indicates that it's for object 2.
Yeah.
Right. Now, what then follows is that the total momentum before the collision in this system is simply P total initial, which equals mass 1 times velocity initial for object 1. So mass of object 1 times the initial velocity of object 1 plus the mass of object 2 times the initial velocity of object 2. In other words, PTI, total momentum that is initial, equals the momentum of the first object plus the momentum of the second object.
Yeah.
Now, we're going to picture that these two objects collide, right? So now there's a collision, smack, the two balls hit each other, and now they've changed direction. Object 2 moves in the direction opposite to where it was going before. So it has now velocity 2, which is its final velocity, or rather it has velocity final, which is its final velocity for object 2, just as object 1 has its final velocity, right? And the total momentum there becomes the sum of the momentum of object 1 and the momentum of object 2. Are we still together?
Yes.
Awesome. Now, after the collision, the momentum is simply P final total, which is mass of object 1 times its final velocity, the velocity final for object 1, plus momentum of object 2, which is mass of object 2 times velocity vector, the final velocity vector of object 2. And the System of the two balls is isolated since there are no external forces acting on the ball. So that's important to note. So isolated system simply implies there are no external forces acting on the balls. So in other words, it's not like as ball 2 was moving toward ball 1, there was a little cue stick hitting it to move faster, you know what I mean? Or a hand slowing it down so that it doesn't move as fast, or a little bump in the cushion, something like that, you know? So there are no external forces acting on the objects. Okay, and then the little table we have there simply just illustrates the conventions for things like direction. So if you're going to take to the right as positive, then the object moving toward the left will have a negative velocity direction. And the same convention is carried out from the start right through to the end. So in other words, before the collision, you choose a convention, you keep at it until after the collision.
Yeah.
All right, so there is a nice example that we can both discuss. It's an example featuring a toy car and a toy train. I'll just note here, word example 8 on conservation of momentum. This is page 41. Conservation of momentum. And the given variables, or rather the given details, are that we have a toy train, choo-choo train, and it's traveling, let's say it's traveling eastward, so to the right. The choo-choo train is traveling to the right at a velocity initial. We'll call our train object 1.
Yeah.
And its initial velocity is 1.5 meters per second. It's positive, so eastward or to the right is positive. And then the toy car is traveling westward, so to the left. And it's moving at a velocity vi of object 2 equals negative 2 meters per second. Right. We're given the mass of the toy train, and its mass is 1.5 kilograms. And we're also given the mass 2 of the toy car, and the car's mass is 1 kilogram. Right. If after the collision, the car rebounds at a velocity of 2.05 meters per second, what is the final velocity of the train? Now, it's important to note, the English says the car rebounds. So that tells us that it actually changes direction. Yeah, I like that you got it. Changes direction, so the sign of the velocity vector also changes. It goes from negative to positive. Yeah. So since we chose eastward or to the right as positive, then we can go to our definition. which is that the initial total momentum equals the final total momentum. Right, so for initial total momentum, we have the mass of object 1 times the velocity initial of object 1 plus the mass of object 2 times the velocity final, or rather initial, my mistake, of object 2. And that must equal the mass of object 1 times the final velocity of object 1 plus the mass of object 2 times the final velocity of object 2. So I'm mentioning the subscripts out loud so that when you get a chance to watch the video as you're revising, you can also take note and internalize how the symbols rather are used in as we're working with the concept. Now we're going to just substitute. We've got the mass of object 1, which is the toy train, and it's given as 1.5 kilograms. And we also have the initial velocity of the train, which is positive 1.5 meters per second, because it's moving toward the east. Now we have to add that to the mass of object 1, which is 1 kilogram, and we multiply that mass of 1 kilogram with the initial velocity of negative 2 meters per second. And we say that this equals the mass of object 1, or rather, let me not use symbols since I'm substituting. The mass of object 1, which is 1.5 kilograms, and the velocity final of object 1 is unknown, but we do have the mass of object 2, which is 1 kilogram, and we do have the final velocity of object 2, which is 2.05 meters per second. That is positive because it's going in the eastward direction. 100%. So yeah, the momentum for object 1 initially is 2.25 kilogram meters per second, and the initial momentum for the second object, the toy car, is negative 2 kilograms meters per second. And this equals, okay, my screen wasn't switched off just yet. And this equals 1.5 kilograms times VF1 plus, I'm just plugging in my computer so that it doesn't go flat-ish. Wasn't fully charged earlier. And then we and then we have 2.05 kilogram meters per second. Right. So on the left hand side of the equation, we've got 2.25 minus 2.
Minus 4.
Sorry?
I'm saying minus 4.
Minus 4. The example in the learning guide might have a few holes in its argument, and we're going to discuss that. That is because the mass of the toy car is given explicitly as 1 kilogram. not 2 kilograms.
Okay. Yeah.
Do you follow?
Yeah.
The mass of the toy car is given explicitly as 1 kilogram, not 2 kilograms. However, if let's say you're in a test and you substitute 2 instead of 1, and you carry on accurately with that 2 instead of the 1, you might get -1 mark for an incorrect answer. But because you substituted correctly and you followed the method and the scientific definition principle or mathematical principle, etc., accurately, you get marks for consistent accuracy. So it's just -1 for the final answer, or -2, depending on really the marking guideline.
Okay.
But for consistent accuracy, you will get more or less full marks for the method. So it's just method marks. So just keep that in mind, right?
Yeah.
Obviously, the goal is to be as accurate as possible. So it's always best to get the correct answer and the correct method. So let's go with correct answer by correct substitution. So 2.25 minus 2 is 0.25 kilogram meters per second. And on this end, we've got, and then we subtract the momentum from the right hand side using additive inverses, I guess. 2.05 kilogram meters per second, and that equals 1.5 kilograms times velocity final of object 1. So now we've got 0.25 minus 2.05, and that gives us negative 1.8 kilogram meters per second. That equals 1.5 kilograms times the final velocity of object 1, and then we divide that by 1.5, and we get the final velocity of object 1 to equal negative 1.2 meters per second, which is it changed direction after the collision. 1.2 meters per second westward or to the left. Okay, so the textbook, the example in step 3, the substitution is likely incorrect based on the information given. And it's probably likely that the authors were like, you know what, we recognize this mistake, but let it be a point of discussion between teachers and learners, etc. Also, I think mistakes in texts like this encourage us who are learning through the material or with the material to have more confidence in our knowledge of the theory. So if we know the principles rigidly, it doesn't matter what information we're given, we can always argue it out based on the first principles that we know for a fact don't change, at least in the Newtonian space that we're dealing with. So we're gonna do the second worked example for conservation of momentum. And then I would like you to do worked example number 10 as homework, but you and I are gonna do 9 for the next few minutes, and then we'll just have a general discussion to close off so that by 8ish we're finished. But we are looking at a fighter jet that's flying at a very high speed. correct example 9 is on page 42. So worked example 9 tells us that a fighter jet loaded with a missile apparently is flying, let's say, to the left, and that direction is positive. So it's flying westward, and it's flying at a very high velocity of 275 meters per second. And as it's flying at that speed, the pilot fires a missile forward, and that missile launches at a speed of 700 meters per second. So object 1 is a jet. And it has a velocity of 275 meters per second. Object 2 is the missile, but we only know its initial velocity, its velocity 2 so far. But we also know its velocity 1. Do you know why?
The same speed, moving at the same speed as the jet.
100%. That's absolutely correct. Okay, that's absolutely correct. But now we're also given that it has a second velocity, which is now 700 meters per second. And that velocity is obviously much faster than the velocity it was moving at initially.
Yeah.
We're also given the masses of the objects. The fighter jet is 5,000 kilograms, and the missile is only 50 kilograms in mass. So now, we can proceed to write our conservation of momentum formula, which tells us that the initial total momentum of the system equals the final total momentum. And the initial total momentum is the sum of the momentum of object 1 and object 2. So momentum of object 1 plus momentum of object 2 initially equals the second momentum of object 1, the second momentum rather of object 1, and also the second momentum of object 2. So M1 is 5,000 kilograms, and that's multiplied by initial velocity of 275 meters per second. We add that to mass 2, which is 50 kilograms times, I guess, 275 meters per second. And that equals, the goal is to find out the new speed of the jet after launching the missile. So what we're looking for is VF1, the final velocity of object 1. So 5,000 kilograms times VF1, we don't know VF1, plus, I'm supposed to put a 2 there. the momentum of object 2, which is 50 kilograms, times we have its final velocity, which is 700 meters per second. All right, so now we do the math. We have 5,000 times 275, and that's 1,375,000.
Izongishaya le nto when I need to use a calculator. I promise you.
You think so?
Yeah.
Nah, let's just hang in there. It's always great to isolate the things. So I started off with multiplying the 5,000 by the 275, and I wrote down that answer as it is. Right, and then I just take down the units as they are. And then also another thing that helps is using the memory function in your calculator. So if you have a multiple step problem like this, you know that you will need the answer for momentum 1 of object 1, momentum 2 of object 2, and momentum 1 of object 2 and momentum 2 of object 2. So those three you can store in 3 memory keys in your calculator. Then as you progress, you just recall the memory items and apply the necessary sums. So that sharp calculator, I know it's got A up to F, so you can store 6 things that you calculate in memory. But we'll do I guess we'll have to make time to do a calculator use class.
Okay.
Yeah. Okay, so then I have the other momentum, which is 50 times 700. And this is 35,000 kilogram meters per second. Okay. So I'm gonna take the 1,375,000 and I'll add it to the 13,750. And that gives me 1,388,750. And then using additive inverses, I'll have to subtract the other momentum, which is 35,000. And I'll get 5,000 kilograms times velocity final of object 1 equals 1,353,750 kilogram meters per second. And then this I'll have to divide by the 5,000. And the final velocity of object 1, or the jet, is 270.75 meters per second, roughly 271 meters per second. And it's in the original direction, there's no change in direction. What does that tell us?
That after it lost its mass, that was the missile, it became less heavier and traveled a bit faster.
Not really. Because the important numbers to note is that the mass didn't change. The mass of the jet remains 5,000 kilograms before and after the launch of the missile. And
the mass of the missile.
The mass of the missile also doesn't change, it still remains the same.
But removing it from the jet, doesn't it make the jet lighter?
The mass that we're given for the jet does not include the mass of the missile.
The mass of the rocket is 50 kilograms.
The mass of the missile is 50 kilograms, yes. But it's independent, and the mass of the jet does not include the mass of the rocket. Those two are defined explicitly like that. That's why we have M1 is 5,000, and that's only for the jet, object 1. And the mass of the rocket or missile is 50 kilogram, and it's only for the for the rocket. But initially, they have the same velocity.
Yeah.
But now we notice that
5.
whilst the rocket has a velocity final of 700 meters per second, the initial velocity of the rocket was 275
175.
meters per second. But after the calculation, or rather the launching of the rocket, and we do our calculation, we find that the velocity of the jet has changed.
Yeah.
Yeah, the direction is still the same, but the size has changed. And it's moved from 275 meters per second to 271 meters per second. So what does that tell us about the impact that the rocket had on the jet as it got launched?
It moves slower.
Which one moves slower?
The jet moved a bit slower.
That's true. That's true.
But-
So, yeah,
Yeah.
carry on.
Mm.
That is 100% correct. So, that simply means whatever the mechanics of launching a rocket mid-air from a fighter jet, whatever the mechanics are, they actually slow down the fighter jet for the rocket to launch at that speed.
Yeah.
So, I don't know, do you have friends who work in the Air Force
I do.
and they fly planes?
Mandisa Mfeka to be exact.
Ask them how the plane feels as it moves once it's launched the rocket.
I can imagine that on launch there is a second drag.
Yeah, a second drag on the jet.
Yes.
Yeah, so
Like a drag for a bit.
yeah, it sort of pulls the jet,
Stalling. Yeah.
because remember, for the rocket to launch, it has to push against something. And it's pushing against the very thing that it's moving with.
Moving with, yeah.
So it'll have to slow it down a bit for it to move at the speed that it should move at.
I'd argue that if maybe the missile was a bit heavier, but yeah, I get.
You get the concept, right? So just find out from your fighter jet friend how that feels when they're in mid-air at high speed and they have to launch a rocket. How that feels. Like, how does the jet feel? Does it move a bit slower after immediately launching, or what? Just try and keep this example in mind and find that out from them.
Yeah.
Yeah, well, then the worked example 10 is kind of also like that. Have you shot a gun before?
Not a real one.
Not a real one.
No.
That's fine. I have friends who have guns, so they always say this about them. Like, there's a kickback force, right? Depending on the type of gun.
Yeah.
So this example will probably touch on that, but I want to give it to you as homework so that you study it as you answer it and you get familiar with how the concepts play with each other. The mass, the velocity, the momentum, the total momentum before and after a collision, right? And I think that should set a nice tone for the next part of the chapter, which is elastic collision. But for the remainder of the hour, we'll just discuss this part here. So I'll leave homework as worked example 10. So please do it step by step.
Yeah.
As homework. Today is 13th Feb. And we had a homework due today, if I'm not mistaken. Yeah.
Dude, I'm struggling with that, yo.
You're struggling with that. Yeah,
Probably
exercise
should
2,
just do it
3.
at work. Maybe I should just do it at work.
Will your employer not have a problem?
I don't know.
Have you talked about your employer about okay, but we'll have this conversation offline. I'm still recording. But anyway, let me discuss this. So we've been applying a conservation of momentum to collisions and I guess explosions, which is valid, but there are actually two different types of collision and they have different properties. So, two types of collisions. The first one is elastic, and the second one is inelastic. Now, in both types of collision, the total momentum is always conserved, right? So, in both cases, P total is always conserved. So the momentum doesn't change. But here's the difference. Do you know what kinetic energy is?
Yeah, sort of, yeah.
So kinetic energy is moving energy, kinesis, right? From kinesis meaning movement. And what they're saying here is that kinetic energy is conserved for elastic collisions, but it's not conserved for inelastic collisions, right? So, however, so kinetic energy is conserved for elastic Girl. You remember the Incredibles?
Yes, I do. Yeah. Even in the Flash.
So we're gonna, I guess, come across these as we go on. But initially, in a collision, the objects have kinetic energy. So they are moving, so they possess that energy of movement, kinetic energy. Now, in some collisions, that energy is transformed through processes like deformation. And in a car crash, the car gets all mangled, which requires a permanent transfer of energy. So, yeah, when you think about it, the energy that a car is moving in before a collision, let's say it smashes against the wall. If the wall is stationary and doesn't break, let's say it's a very thick wall, and the car smashes into the wall that it becomes so flat it's like a pancake. Where did all that energy go? It's food for thought. But the long and short of it is that for the car to deform, that kinetic energy changes from movement energy to the mechanical energy that actually changes the physical properties of the car from an actual car before the collision to what seems to be a pancake thing after the collision. So all that kinetic energy gets transferred from one form to the other into a sort of physical energy that changes the form and shape of that vehicle. So that's
Yeah.
the permanent transfer of energy. Alright, so the next class we have, we're going to discuss from elastic collisions.